Going to be here for just a bit. Let's take a look at this stuff. So 1.3 was this is the section, this is the distance formula section. The hard stuff from 1.3 is the distance formula. All the meat of that section is there. So I mean, in the problem set, you're going to have just a couple of other questions that deal with a few other things. Relatively minor though, but we haven't talked about it yet, so I want to just fill in the gaps here just a bit. A vocabulary term that we need to be familiar with in math in general, but probably mostly so in geometry, is the word postulate. In geometry, rules that are accepted without proof are called postulates. Rules that are proved are called theorems. So what we're going to do a lot in math, and especially in geometry, is we're going to utilize theorems and postulates to prove other things. Those are statements that we know to be true, either that we've proved to be true in the case of theorems, or somebody's proved them to be true in the case of theorems, or postulates that are just so basic that no proof is required. We just all accept it as being true because it's so obvious. Okay, now there's two of those we want to talk about today, two postulates. One of them is really simple. The ruler postulate essentially just says it's okay to use a ruler to measure distance. That's all it does. It justifies using a ruler to measure distance. Now let's say this. Let's say I've got these 2 points, A and B, on this line AB. If I want to find out how far apart they are with a ruler, let's say I do this. I put a ruler up next to this line, and one of the marks on the ruler, right here, is at 25. And one of the marks on the ruler, right there, is at, say, 37. How far apart are those 2 points?
12.
12, I did that. Exactly, you subtracted. That's the ruler postulate. The ruler postulate just says that if I put a ruler up next to 2 points, I can measure their distance by finding the difference of the marks on the ruler. Okay? Now, I could either say 37 minus 25 is 12, or I could say 25 minus 37 is negative 12, and take the absolute value of that. Either way, right? And so technically what we say is the ruler postulate tells us that the distance between A and B is the absolute value of their difference, just in case we subtract in the other direction. But we don't have to, right? We can always just conveniently subtract the small number from the big number, right? So that's the ruler postulate. No big deal. Okay, this is a little bigger deal. Before we jump into the next postulate, there's one little issue we have to confront. In terms of geometry here, we would say that point B lies between points A and C, but point E does not lie between points D and F. Okay, what's the difference? It's one thing, Drew.
E is not on the line. B is.
Okay, E is not on the line that connects D and E, right? But B is on the line that connects A and C. So that's one thing that has to be true. It has to be on the line. And then the other part of it is it has to be between the two endpoints. Meaning, if an ant starts at B and walks towards A, he's walking in the exact opposite direction that he would walk if he started at B and walked towards C. Make sense? Yes, sir.
Can the point be anywhere in between?
Could be anywhere, anywhere. As long as it's on the line, and ants that were setting out for A and C would be moving in opposite directions. But B could have been down here, if that's your question.
Or B could be like right up next to it.
It could be right up next to A, exactly, yeah. It doesn't have to be in the exact center or even near it. There's someplace on that interval between A and C. Okay, and what this allows us to do then, it allows us to come up with what's called the segment addition postulate, which is very straightforward. It just says this: if B is between A and C, or really I should say if point B is between points A and C, then the distance from A to B, and that's what that means, right? And A next to a B means a distance. The distance from A to B plus the distance from B to C equals what?
A to C.
A to C, sure. It's like taking a pit stop on a road trip. Right, if I'm driving in a straight line towards somewhere on vacation, if I drive from A up to B and then I take a pit stop and eat a burger and I get back in the car and drive to C, well, if I just add up the distances that I traveled during the first part of the trip and the second part of the trip, it's the whole trip, right? So there's the segment addition postulate, okay? No big deal. Very straightforward. No, so we're done with that stuff. Now here's the more fun part. Okay, on the distance formula assignment, I told you there were some real doozies near the end. This is one of them. This is one of the problems that I think is pretty tricky. Now, I want to talk about. This is a really cool problem. This does an awful lot to get you ready for Algebra 2. You're going to be thankful next year that you did some of this stuff. Okay, so what does this say here? Let's read through this problem. If point A has coordinates -5, 3, and point B has coordinates x, -5, and AB, the distance from A to B is 17, find the values that x could have to make that true. Now, what's that mean? If we see a variable x in there for one of the coordinates, yeah, it's unknown, right? We're going to have to find it, right? But it's unknown. It's variable. We don't know what that is. We know the precise location of point A, but all we know about point B is that its y value is -5, right? Okay, now that's kind of strange, right? Let's draw a picture here to represent this and see if that helps a little bit. Okay, so let's put point A on this xy plane. How do I get to A from the origin? Left 5, so I'm going backwards in the x direction 5, and up 3. So right there. Okay, so there's A. Whoops. There's A. Okay. Now what about B? Yeah, I don't know where the x value is. So let's find some representative points. If I want to represent all the different places that point B could be, what would those be? Somebody name a place up here I could graph that's one place that point B could be located at. Okay, it could be over at -3, -5. So it could be right there, couldn't it?
It could be anywhere as long as
So what's that going to look like? What are all the places with y coordinates of -5 if I connect those all into one shape? I'm seeing some of this, horizontal lines, right? All these points here have y coordinates of -5. If I just connect them all with a nice smooth line, that's a pretty smooth line. There are all the possible places, right? Now, what about the second part? If I want to find only the places that are a distance of 17 away from A, how's that going to work? Let me give you another quick example that'll help you with this maybe. Let's take a little simpler situation. What if let's say I've got a point right on the origin, and I want to find all the places that are a distance of 3 away from that point. Just let me name a couple places that are convenient. Give me the location of a point that is a distance of 3 away from the origin. 3, 0, sure. I could go over 1, 2, 3, and there's a point. There's another one. 0, 3. I could go up 1, 2, 3, and there's a point right there. 0, -3. So 0, go down. That's also a distance of 3 away. -3, 0. Is that it? Just 4? This one's a little bit off. Okay, are there some others? They might be harder to find. You may not be able to tell me exactly what they are. But wouldn't you agree that they're there somewhere? It's not as easy as just going over this. Needs to be calibrated. It's not as easy as going over 2 and up 1, for example. That's not going to work just right. The other ones are going to be real inconvenient. They're not going to be nice integer answers. But isn't there one about there-ish, maybe? Maybe one about there, maybe one about there, about there. There are more, though. If I connected all of those possible places, what shape do they make? Circle. Sure, doesn't that make sense? Because, like, if a dog is running around, little stakes you put in the ground, if the leash that the dog is on is 20 feet long, that dog can go any place inside a circle that's 20 feet from the stake, right? In fact, that's really the most basic definition of a circle. We'll give it some fancier definitions later in the year, but really the most basic and simple is a circle is the set of all points that are equally distant, the same distance away. We say equidistant from a given point, the center, right? So there's one point in the center, and then all the other points on the circle are just the set of all those points the same distance away. So let's draw that. Like that-ish.
What's your calibrator?
I think I need to. It's drinking that.
No, it takes like 30 seconds. Yeah. Who needs to be obsessed with calibrating?
Quandon?
Yeah, he used to do like every other second. Oh, we need to recalibrate.
Much better. So there's my circle, right? Radius 3, those are all the points at distance 3 away from 0, 0. Now if we go back to our picture, what am I going to do here? If I want all the points at distance of 17 from point A, what do I do? Yeah, make a circle with a radius of 17, right? Now 17, that's big. There's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So right about that far away, something like this, maybe. Let's try that. Well, you get the idea. Something like.
Did you really see that big?
Yeah, about like that, right? And so you can see visually on here that I'm going to get two places, aren't I? I'm going to get a place right there, right? There's one of them, where the y value, the y coordinate is -5, and that distance is 17. You know, it's not perfect probably, but, and here's the other one over here, right?
If you went to the right, like.
Oh, that's not even close, is it?
No.
But you get the idea, right? There's going to be two of them on there. So now we can kind of see geometrically that they're there. But geometrically, we don't get the answers. We just see that how it has to be set up so they could be there. And this often happens in math. We can go to a graph or a picture or a geometric sketch like this to sort of get a feel for how the problem works. But then to get an actual answer, we've got to rely on algebra. So how do we do the algebra? This
Can't
is.
you just set it up like almost like do the little.
We're going to do the distance formula. That's what we're going to do. Because we're talking about a distance, aren't we? Right? So if I want to find the distance from, well, first of all, tell me what's my formula for the distance between 2 points. Okay, the square root of the quantity x2 minus x1 squared plus y2 minus y1 squared. Good. And so we've got stuff we can plug in for all those, right? We know that the distance, this is just d, right? 17. That's going to go there. Here are my two x values. Here are my, or excuse me, there's my x and y and x and y. Now, this is a minor point, but it's helpful to be careful about this. Which one do we want to call x1, y1, and which one do we want to call x2 and y2? Keeping in mind that we're ultimately going to be solving for x, so we want the x to fall in a convenient place in our equation. Yeah, so I guess what I'm saying is, do I want to subtract these numbers from those numbers, or vice versa? Wouldn't I rather say something like x minus -5 instead of -5 minus x?
Yeah.
Does that make sense? I mean, both ways will work, but doesn't that make sense? Where we want to make the x positive. So let's go ahead and call these points 2 and those points 1, right? So x1, or excuse me, x1, y1, x2, y2, right? So then that's going to become, if I plug all this stuff in, the d becomes a 17, the x2 becomes an x, the x1 becomes a -5,
Ching chong.
right? So bing bong,
Oh,
minus -5.
Still learning.
and then the y2 would have to be the negative 5, right?
Still easy.
Minus 3. You see what I'm doing?
Yeah. So we're pretty much doing the same, except now we have the x instead of the d.
Yeah. Right? So the only different now, so we got everything in there, but this time what's left over that we're solving for, the variable, is the x, right? But remember what we did at the beginning of the year. This looks an awful lot like the stuff we did at the beginning of the year when we solved for x by isolating, right? I told you that if you can point at a single x, you can always isolate it. It's the truth, you can. So we should be able to isolate this x if we just reverse the order of operations and carefully go through the steps. Now before we do that, let's see if we can clean this up a little bit. Like I'm kind of stuck with the 17 over there, but what about all that stuff right there? Can I turn that into a single number?
Yeah.
Sure. What's negative 5 minus 3? Negative 8. And if I'm going to square it, I might as well make it
4. Oh.
positive 8. Okay, what is 8 squared? 64. Okay, good. So we can rewrite this then as 17 equals the square root of x plus 5 squared plus 64, right? Now I just got to get that x by itself, so we'll just reverse order of operations, just like we did before. And what's good about this problem, this is a great Algebra 2 problem, is that as we work our way through the order of operations, when we get to the top, sometimes we got to just go to the bottom and start again until we keep cycling through it until we're done, right? So the first time through, is there any addition or subtraction outside of the square root to deal with? No, nothing. Any multiplication or division outside of the square root? No. The first thing we see is that square root. Now, how did we say we deal with square roots at the beginning of the year? Where does a square root fall in this scheme? Exponents, good. So when we get to the exponent, because it's really a 1/2 power, right? So when we get to the exponent, that's the first thing where we do something is we got to deal with the square root using exponents. What could I do to get rid of a square root? Square it, right? I know that if I square a square root, that cancels the square root, right? But I have to treat both sides equally because it's an equation. So we'll just square both sides. So if I square this side and I square that side, the square and the square root cancel, and everything inside the square root then is set free. And so we end up with what? Well, 17 squared is 289. And so over here we've got our x plus 5 squared plus 64. Okay, so we'll continue with our order of operations. We go up to parentheses. Let's see, inside the parentheses there's nothing I can do because the x and the 5 don't combine. Yes, sir?
Don't you get rid of the square?
We're going to, you're right. So we made it to the top, and we still have some stuff to do. So we're going to turn right around and cycle through again. Right? So we'll go down to the bottom and start again. What about, is there anything we need to add or subtract to get the x by itself?
64.
Subtract 64. Good. Yeah. So, okay, and that's going to give us 225. Oh, what happened there?
Ooh, you just messed it up.
What did happen there?
Dude.
You need to calibrate me.
Something happened.
That's Quinn's style of fixing everything. Let's recalibrate it. That should fix it.
All right, well, let's see. Maybe it's okay now. So 289 minus 64 is 225. The 64 minus 64 obviously cancels, and so I get x plus 5 squared. Okay, now what? Square root, right? Good. So if I work my way up, no multiplication, but there's an exponent to deal with. I got to get rid of the square root. Now, how do we supposed to get rid of the square? How do you supposed to get rid of something squared?
Square root.
Square root it, right? Okay, so let's do that. Now, this is where we got to be a little bit careful though. This is where things get a little bit weird, and this is where we really enter more of the Algebra 2 world. So I'm gonna go to the next page. Give myself a little room. Okay, let's flip this around. Put the x's on the left. How about? So I've got x plus 5 squared equals 225. Now, what about this? If I've got x plus 5 squared equals 225, how am I going to undo? You told me I square root both sides, right?
Yeah.
So if I do that, if I square root both sides, that's going to give me x plus 5. But what are the numbers that could be multiplied to give me 225? Well, 15 is the square root of 225. So 15 times 15 would do it, but what else would do it? I could multiply positive 15 times positive 15 would get an answer of 225. But I could also multiply negative 15 times negative 15, right? And so what happens when we're doing this process of isolating a variable, and I square root both sides, and we'll do a ton of this next year. When I square root both sides, I have to put a plus or minus in there when I take the square root.
I would have stayed in algebra, would I not have been able to graduate?
What's that?
I would have stayed in algebra, would I not been able to graduate?
I don't know. That would have been a crime for you to stay in algebra. I mean, because you should be in, are you junior?
Yeah.
So good. Get out of two next year. That's good. Okay, so now look what happens here. How many answers are we going to get? Instead of just getting one like we normally do, how many are we going to get here? 2. I got 2 different cases. I got to take the case where the 15 is positive and the case where it's negative. So let's take the positive case. If we take the plus 15, look what we've got. We've got x plus 5 equals positive 15. So what is x if I solve for x? 10 if I subtract 5 from both sides? Good. So x equals 10. Now what if I take
X equals negative 20.
the negative case, right? Then I've got
Right.
x plus 5 equals negative 15. So
X equals negative 20.
if I subtract 5, x equals negative 20. Good. Okay, and so so now we know the locations of those 2 places, right? Where that big circle with the radius of 17, where it hit that horizontal line. It happened at x equals positive 10 or x equals negative 20.
So those are the 2 answers.
Those are the 2 numbers. You got it.
Yeah, that was all. Not move on something. No, you just had to.
Okay, so the greatest value would have been 10, the least value would have been negative 20, right?
Okay,
A lot of stuff. Okay, let's
Let's
go work.
You know what? It's kind of like a suspension.